Hello everyone. In this video, we are doing the solution to the fifth problem from INMO 2024. So in my opinion, this is a very beautiful problem and solving this will help you gain very helpful insights into how geometry works and especially how rotations works in a plane, in a Euclidean plane. So let's first read the problem condition. So we are given 3 points A1, A2 and A3 which lie in a circle delta, gamma. So this is the circle gamma in counterclockwise manner. So these are the points A1, A2, and A3. And we are given rotations about A1, A2, and A3. So tau 1, tau 2, and tau 3 are three rotations. And how are these rotations defined? They are basically, suppose we try to figure out how T1 works. So what we do, suppose there is a point P, suppose there is a point Q. And what happens is the point Q is rotated to a point Q dash, say a point Q dash about A1 such that this angle and this angle are the same and these two line segments have equal length. So this is basically how rotation works. T1 and similarly T2 and T3 are different. So next let's try to read the problem statement. So it says that we first do transformations Ti plus 2, Ti plus 1 for all values of I1, I2 and I3. So we obtained 3 points basically which are P1, P2, and P3, and we are asked to prove that the radius of the circumcircle of P1, P2, P3 is at most the radius of gamma. So basically what happens is we are given a triangle A1, A2, A3, and there is a point P in the plane, and first we apply, say we figure out how T3 of T1 of T2 works. So T2 of P is basically we rotate about A2. So we rotate about A2. So what happens is there is a rotation going on about A2. This angle is angle A2, where this angle is also A2, and we end up with a point say P dash, and then again we rotate this point P dash about A1. So suppose we get P dash, and P dash we again rotate via A1. So this becomes P double dash, and this angle is basically equal to this angle. And again this point P dash we rotate about A3 and we get P triple dash, and this P triple dash is basically tau 3 of tau 1 of tau 2 of P, and this is defined to be P1. This is how we obtain the point P1, and again we obtain two more points P2 and P3, and we are asked to figure out the radius of the circumcircle of P1, P2, P3. So this is basically the problem condition. So before diving into the problem, first let me put forward a couple of lemmas. So let's proposition 1. So here I will discuss the concept of homothety. Suppose there is a triangle. Suppose this is a point O and these are points say A1, A2 and A3. And suppose we construct three more points by joining OA1, joining OA2 and joining OA3. Suppose we construct three more points, say B1 and B2 and B3. And how are these points constructed? Basically, these points are constructed such that these two line segments are equal, these two are equal, and these two are equal. So basically, OA1 equal to A1B1 and so on for the all three coordinates. Then a very clear observation which maybe most of you will see that this triangle is similar to this triangle. Okay. So to prove it formally, what you can do is suppose we draw a coordinate system centered at O, and suppose A1 has the coordinates x1 comma y1. Then by the construction B1 has the coordinate 2x1 comma 2y1, and so basically using this, and B2 will basically become equal to 2 say x2 comma 2y2, and B3 will become equal to 2x3 comma 2y3. So this basically B1, B2, B3 will become similar to A1, A2, A3, and the ratio of similarity will become equal to 2. and the ratio is 2. And this basically means that if we consider the circumradius of this circle and the circumradius of this circle, suppose we say that this radius is r and this radius is say small r, then we basically obtain capital R equal to 2 times small r. Okay, this is the condition we obtain. This basically is known as homothety. This is the first concept I want to bring about. The second concept is, say we write proposition 2. Let's try to understand some properties of rotation. Suppose we have a center of rotation O and say every point is rotated by an angle alpha. Okay, so alpha is the angle of rotation. Alpha is the angle of rotation. And suppose we consider a line. Okay, so suppose this is the line L. So what happens to the points in this line under the rotation alpha? Okay, so what happens is this line basically gets transformed to another line, say T of L. We are naming this transformation as T. T is the transformation with angle alpha and the center O. Okay, so this line will get transformed to another line T of L, and the angle between T of L and L, so basically this angle will become equal to alpha. This is not very hard to see because if you imagine using some animations, this angle will become equal to alpha. Okay, so this is the second proposition. So in particular, let's observe what happens to a line under the transformation given in the problem. So let's try to see what happens in T2 of suppose the line L. So basically we are first rotating by the angle A2, then we are rotating by angle A1, and then we are again rotating by angle A3. So these are the angles of rotation. And we know that in a triangle, angle A3 plus angle A2 plus angle A1 is equal to 180 degrees. So this original line will get transferred to another line. Say we are given a line L. The line L under this transformation, tau 3 of tau 1 of tau 2 will get transformed to another line. Say we write T of L, and this T of L will be at an angle 180 degree from the original line, and 180 degree is basically the same as 0 degree. So basically we can conclude that these two lines are parallel. Okay. And another thing to notice is that suppose we are given 2 points A and B. Under a transformation, say we are given T of A, then first of all the point T of B will shift its position from the right of A to the left of A. This is because suppose we are given 2 points in a line and under 3 consecutive transformations, this is basically what happens. So this is suppose A, B, this is A dash, B dash, A double dash, B double dash, and A triple dash, B triple dash. So basically their original positions change. And another thing to note is that all these four distances will become equal. So AB is equal to A dash B dash equal to A double dash B double dash equal to A triple dash B triple dash. This is the second proposition I want to say. And these four distances are equal because under a rotation, the distance between any 2 points doesn't change. This is basically a simple property of rotation which we can prove very easily. Hence, we conclude that tau 3 of tau 1 of tau 2 of say AB, the distance, say we write distance of these two will become equal to the original distance AB. Okay. So this was the second proposition. And the third proposition, this is the last proposition which will help us to solve the problem. Let's notice what happens through the tangency points of the in circle and under a rotation. Okay. So suppose this is the point D and this is ABC. Now notice what happens to the point D under rotation by angle B. So this is angle B centered at B. So this is basically tau 2 in the original problem. Suppose we rename it as A1, A2 and A3. So this is angle A2 and tau 2 of D, suppose we name this DEF. So it is very easy to notice that tau 2 of d will become equal to f. Why is this true? This is because we know that this line segment has equal length as this line segment because the lengths of two tangential points are equal. And also we know that angle A2 is the angle between D and F. Hence, under the rotation at the center A, suppose we center a rotation at A2 and we do it at angle A2, and this we define as tau 2. So tau 2 of D will become equal to F. Okay. And what happens to tau 1 of F? Tau 1 of F will basically become equal to E, and tau 3 of E will basically become equal to D. So this means that tau 3 of tau 2, sorry, tau 3 of tau 1 of tau 2 of F is basically equal to F. So this is the last proposition I want to discuss. Okay, so this means that the point F is invariant under the transformation tau 3 of tau 1 of tau 2. Okay, so now let's return to the original diagram I had. Suppose this is the point P and these are points P1, P3 and P2, and let's consider what happens to the point P2. Okay, we know that under the transformation, tau 2 of tau 3 of tau 1, the D2 point will remain fixed at D2. Okay, point D2 will remain fixed at D2, and hence consider what happens to the point P2. Suppose we write tau 1 of tau 2 of tau 3 of P is equal to P2. Then notice that first of all, consider what happens to the line D2P. Okay, the line D2P will be, let me make it clear. So the line D2P, this line will get transformed to a line parallel to itself as I have proved earlier, and this is basically T of D2 and this is T of P. Okay, and basically T of P is equal to P2, and notice that as I had proved earlier, T of D2 is basically equal to D2. So this is the point D2, and this basically means that we also know that these two lines are parallel, and this is the point D2, which means that the point P2 lies somewhere here. So this is where point P2 lies by the all the claims above. So point P2 lies on the line segment PD2. So this basically is a whole line segment, and also I had proved that this line segment is equal in length to this line segment. So by this we can conclude that P2 is the reflection of P over D2. So if we place a mirror at D2, so P2 is the reflection of P over D2. So now comes the first claim I had proved. So if we consider P as origin, then these points P2, P1 and P3 are basically dilations of the point D1, D2 and D3. So what we can conclude from this is that the circumradius of P1, P2, P3 is twice the circumradius of D1, D2, D3. This is the last step. So we get that radius of P1, P2, P3 is twice the radius of D1, D2, D3. And note that the radius of D1, D2, D3, this is basically equal to the in radius, which we denote by small r. So small r is the in radius. And we need to prove that 2r, which is the radius of P1, P2, P3, is less than the radius of gamma, less than equal to the radius of gamma. And the radius of gamma is the circumradius. Okay. The radius of gamma is equal to the circumradius. So this is what we need to prove. So what we are left is, we are given a circle and we are given 3 points and there is an in circle. So we need to prove that if this radius is equal to r and the radius of the larger circle is capital R, we need to prove that 2r is less than equal to capital R. And For this, I will use a well-known inequalities. So consider, suppose this is the in center I and this is the circumcenter O. So OI square is basically equal to R square minus 2RR. Okay. So R square minus 2RR, and obviously OI square is greater than equal to 0. So this means that R into R minus 2R is greater than equal to 0, or in particular this means that R is greater than equal to 2R. This is a very well known inequality, that OI square equal to R square minus 2RR, and you can look it up in the internet to find a proof of this as well. So this basically proves that 2R is less than equal to R, and we are done with the problem. So thanks for watching the video.